So thank you very much, Jacopo. First of all, I would like to thank the organizer for giving me the opportunity to give this talk, and thank also Alessio for winning the Fields Medal, which also gave me the opportunity of giving this talk. And since this is an opportunity to celebrate a unique event like Alessio's winning the medal, and before passing to the mathematics, I would like to, I don't know, put some picture on which reminds us how good were the old time where this meeting could be presential, right? So, I mean, instead of complaining that we cannot do it presentially, I prefer to be optimistic and say, okay, let's remember the old time and let's hope they will come soon back again. And so the first pictures, the first set of pictures is, I mean, these pictures are taken over the last 10 years, no? So we start in 2010 at the meeting in Banff, and you see here Alessio was pretty young. He is still pretty young, but it was 10 years ago here. And then the year later, in 2011, we organized a school in Santander, and Villani, Otto, Maria Esteban, and Carrillo were the speaker. The organizer was Juan Luis and myself. And Alessio was there as a keynote speaker. He didn't give a course at the time, but we made the terrible mistake that we amended in 2016 in Cetraro, right? I mean, Gabriele and myself organized a course there in Cetraro, and Alessio was one of the five people who made a course there. And then after this, I remember also with a lot of nice feelings, the Austin recurrent event. I was visiting frequently Austin when Alessio was there, and the Austin frequent event was Alessio's birthday. I mean, I was visiting in spring around his birthday, and there was always the nice occasion to celebrate it. But in these occasions, you see, we had also the privilege of having a top-level barbecue lesson by one of the biggest experts in the ETH equation, right? Luis Caffarelli, who explained us the secrets of applying the ETH equation to asadito, to the barbecue. And as you can see, a year later, we have experienced what Francesco in his wonderful introductory video told us. No, there is always the possibility of a slight difference between the theory, you see, everything is smooth, here's infinity, say, and the practice, okay? So here, you see, we're contemplating the problem as if it was a combustion problem. I mean, maybe we took the wrong equation, right, Alessio? Okay, after this small parenthesis, then I would like to show a couple of pictures about the event that brought us here, which is Alessio winning the Fields Medal. And these two pictures were taken in Rio right after the award, like right after Alessio received the medal. And here it was after the medal, when we were celebrating in the lobby of the hotel. As you can see, I tried to include pictures of all the people that are present here in the conference and much more, but it's hopeless to find a nice picture which collects everybody. And then one thing that I always like to say is that around Alessio there is always a positive atmosphere. We were always very happy to celebrate him about the medal, and there is always, as I say, a positive atmosphere. And I certainly can say that this thing lasted, because, for example, last year when he was awarded in Barcelona doctorado honoris causa in the UPC, we had this wonderful meeting, and it was very nice. We had this round table, and as you can see from the faces of the speaker here, it was really nice. So after this, let me go back to mathematics, and let me explain you what I'm going to tell about. Is a work that recently appeared in CPAM with Alessio, and it's about the asymptotic of the fast diffusion equation on bounded domains. No, we will start with a brief introduction. I will explain a bit the problem and make connection with the ETH equation, porous medium, let's say introductory part, and then I will state the problem and I will see what are the difficulties in describing the asymptotic behavior of such a fast diffusive equation, and then try to go a bit in the proof. Let's see if the time allows it. Let's see how much we can go into the details. So let me start by presenting the problem. Now, the problem is a nonlinear diffusion equation like this. We put this coefficient just now to explain what happens for all m in R. And let me say that, okay, the simplest example is you put m equal 1 and you recover the ETH equation, and existence, uniqueness, and the theory is well understood. I will spend some time later just to remind you the classical theory, but this goes back to Fourier essentially. Then when you take m greater than 1, you are in the so-called porous medium regime, which is what we call slow diffusion, and a phenomenon of finite speed of propagation appears. I will try to explain you in a second what happens there, but let us concentrate in what we call the fast diffusion range. It means m is between 0 and 1, and here, oppositely to the slow diffusion range, there is not finite speed of propagation. On the contrary, the difficulty is that solution can extinguish in finite time. And if you are a bit expert in, or not expert, if you know something about parabolic equation, you know that there is a problem when the density goes to 0, right? And so this is really problematic for regularity and for a number of things we are going to describe in the rest of the talk. Then let me say that if you want to study m less or equal than 0, well, you see, I mean, there is this coefficient here that now is negative, otherwise the equation is backward parabolic and it's another kind of problem. But you see, here we are studying the diffusion equation, then initial datum, and 0 Dirichlet conditions. Well, there is a result of Juan Luis Vasquez of 1991 that says that here the problem is that solution failed to exist. So L1 solution do not exist, and in general, non-negative solution to this problem when m is negative do not exist, including the m equals 0 case, which is the logarithmic case. Okay? And so in this case, we already explained everything. Solution do not exist. So let me go to, let me talk a bit about nonlinear diffusion, and I would just write a couple of things in order to, for the non-expert, to understand what we are talking about. If you take a general diffusion equation, say the simplest one you can imagine, here you just put the diagonal matrix with the diffusion coefficient, right? And you put U. So this is called the diffusion coefficient. And well, when A is identically 1, we are in the case of the ETH equation. In the case of the ETH equation, we will go back here. We will go back to this case in a while, but let me tell you, there is a whole family of equation which is close to the one of the ETH equation. For example, the ETH equation with A equal 1, it means propagation, for example, it models, for example, propagation of heat in the vacuum or in an heterogeneous media. Then you may say, A is almost constant, so it's trapped between two constants, lambda, small lambda, big lambda, the uniform parabolic, say. Uniform parabolic coefficient. They can be bounded measurable, but they are always trapped between two constants. In this case, you model temperature in heterogeneous media. No, the media can change, and the evolution is still governed by something similar to the ETH equation. Then, when you want to study, for example, density-dependent diffusion, then A may depend on U. And probably the simplest example is A of Tx equal U to the m minus 1, which is the power nonlinearity that we have seen in the first slide, right? And here we fall off sometimes the uniform parabolic setup in the sense that the density, well, what happens when u is close to 0? Well, when u is close to 0, and for example, m is greater than 1, then A again is more or less 0, and the diffusion stops somehow, no? Diffusion is not really stopping, but it slows down a lot. And this is basically the reason why we have finite speed of propagation. Finite speed of propagation means that if you start from a compactly supported initial data, you stay compactly supported for all times. So this is something that, for example, in the ETH equation doesn't occur. What happened in the fast diffusion regime? In the fast diffusion regime, here for simplicity and through all the talk, we will consider only non-negative solutions. When m is less than 1, then when u is 0, then A is more or less infinity. So it's super diffusive. And the mass is lost at a very, very high rate. And so this causes the extinction phenomena. Extinction in finite time. And this is one of the major difficulties of this problem. I mean, after a time capital T, U is identically 0. We will see this thing later on, but I wanted to explain you the heuristic in the equation by discussing the diffusion coefficient. Okay, so now let's see example by example what is known. No, so if you take the ETH equation, the standard ETH equation, then it goes back to Fourier series, the most classical of the Fourier analysis tools, and basically you can prove a representation formula. You can represent the solution of the ETH equation in terms of eigenfunction of the Laplacian and eigenvalues of the Laplacian, no? And Fourier coefficients, the projection on the eigenfunctions. From this formula, it is quite simple to see what happens for large times. Indeed, you see that if you properly rescale in time, or if you properly zoom the solution, then you see that this quantity converges to a constant, which is the first Fourier mode and the first eigenfunction of the Laplacian. Actually, this is better written in relative error. I mean, the quotient between separation of variable solution and the solution minus 1 converges to 0 with this rate. And lambda 2 is the second eigenvalue. This is the second spectral gap. How do you do this? Well, you just collect e to the lambda. You just collect this quantity out of the series, and you just have to prove that this quantity is bounded. I mean, it's not trivial, but nowadays it's considered the standard. What do you need to know? You need to know the second spectral gap and the fact that the eigenfunction behave at the boundary. Remember that they're both 0, phi k and phi 1, so they behave at the boundary like in the same way, so that this stays bounded. Good. Well, this is a sharper result, and it relies on representation formula, which is this one, and spectral analysis, basically, and basic spectral analysis. Well, essentially, can we do it only for the Laplacian? No, essentially, a very large class of operator can fall into this scheme. For example, all the operators that have a compact inverse. We will see an example of operator with weights in this talk. So just for say younger, let me explain you how do you get the representation formula. You use the separation of variable ansatz. You separate variables and you look for solution u of tx, which have the following form. They are a function of time. Sorry, time here has to be tau for reasons that you will understand in the rest of the talk, because then we change the scale. And then you put a certain function of x. No? If you want this to be a solution of the ETH equation, you have that dtu, which is t prime times phi, has to be equal to Laplace of u. But what is the Laplace of capital U? The Laplace of capital U is is t times the Laplace of phi. No? So you come out to the uncoupled system, which is t prime. You want to put it may be equal to minus lambda t, and then if you substitute here, what you get is that minus Laplace of phi is equal to lambda phi. So this is very easy to solve, and it tells you that t of tau is equal to t of 0 e to the minus lambda tau. And this is provided here. You need spectral analysis, a bit of spectral analysis, to say that there exists a family of eigenvalues and eigenfunctions, discrete family of eigenvalues and eigenfunction, and that's it. And phi k is a basis in L2. It's an orthonormal basis if you renormalize them and so on. So basically, now you want to understand what happens to the projections or to the orthogonality condition. I'm explaining this because we will use it in a slightly more complicated setting in the rest of the talk. So what do you do now? You take the time derivative along the flow of the projection. What is the projection? Is projection of the solution against one element of the basis, and this is the L2 product. So this is what you can, let's assume we can do all the manipulation we want. We always have the necessary regularity to do this, the sufficient regularity to do this. And so this is d tau u times phi k integrated on omega. Then here we use the equation. We use the equation, and here we have the integral of Laplace of u times phi k. Then we do what is one of our favorite operation, which is integration by parts. We integrate by parts twice. We can do it because both u and phi are 0 at the boundary, and what we get is u Laplace of phi k. Now we remember that phi k is an eigenfunction. So what you get here is minus lambda k integral of u of tau phi k. Now, reading these and these, we easily conclude that then u tau against phi k, the integral, is equal to e to the minus lambda k tau, the integral of u0 phi k. Okay, once we have this, it is very easy to find the general solution to the equation. Why? Because we just have to project it. Okay, I mean, you write ut as u tau, sorry, as u tau phi k. You represent it in the orthonormal basis of L2. But then what do you use? Then you use this. And you get.
Sorry, you need an extra phi k in the representation.
Sorry. Yes. Sorry. Oops, sorry, I completely missed an extra phi k. Thank you, Robert. Phi k of x. And let me write it correctly. This is u of tau x. Thank you, Robert. And now you use star, and you just get the representation formula. So you get u0 phi k in L2, and then e to the minus lambda k tau, and then phi k of x. And this is the representation formula. And from this, you easily deduce what we wrote in the other slide, which you can easily do this computation once you know a bit more about the spectral, about the eigenelements of the Laplacian. But this is classical. Okay, so what happens with the porous medium equation? Well, with the porous medium equation, we repeat the ansatz of separating variables, and we see that we can find a separation of variable solution of this form. Okay, so the time here is no more exponential because the ODE is different. And then S of x is the unique solution to this problem. Okay, this problem, remember, m is greater than 1, and the constant c is just this one, it's just numerical and this positive. Okay, so S is the unique solution to this semilinear equation with 0 boundary data. Good. You have this, and why this represents the asymptotic behavior? Well, there is a work to do, and let me call that this is called friendly giant, and this terminology was introduced by Dolberg and Koenig in the 80s, because if you look, what is the initial data of this solution? Well, the initial data of this solution is plus infinity. And so this is the biggest solution that attracts all the other solutions in this case. Okay, then what do you do? Well, indeed, you want to show that any solution behaves like this when t is large, when tau is large, but you know, both depend on time. So you want to rescale the variable such that the separate variable solution becomes stationary. So what do? You do a logarithmic time rescaling. You do a rallenting in time to see the slow motion effect, and the price you price that in the equation, the price you pay is that in the equation this term appear. No, so you have a reaction term. You have a certain constant, which is this one, and then you have a W here. And okay, of course, now the separate variable solution is stationary. Okay, then you can do several things, and you can prove a result like this. So that in rescaled variable, the relative error converges with rate exactly 1. This, I mean, e to the minus t, it is a sharp rate. In original variable, this means this estimate. So this estimate is a bit more accurate than what I wrote here, because here we say, for all tau greater than t0, that can be quantified. This is a kind of waiting time you have to wait to enter into the asymptotic regime. Okay, so when we say large time, we will say time larger than a certain t0, which may depend on the initial data. The worse the initial data it is, the more you have to wait for the regularization to take effect and go towards equilibrium. This is a bit the philosophy. So the decay rate is sharp, as you can realize by taking another solution of separation of variables. If you plug this here, you will realize that it is sharp. So these results were obtained by Aronson and Pelletier in 1981 for smooth initial data, then generalized by Vasquez in 2004 in a very nice paper in which he also showed an entropy method to prove these kind of things. And then we gave a quantitative proof more recently, also for non-local evolution or evolution with the coefficient and so on, in a work with Alessio, Yannick, and Juan Luis in a series of papers. But this is not the subject of this talk. I just wanted to tell you what happens in the other two cases. No? So let me just introduce some properties of the fast diffusion equation in order to understand the difficulties. But before doing that, I would like to switch to the blackboard. I prepared the blackboard, even if it is not properly a blackboard, in which I would like to show you what happens at small times and the big times for the ETH equation and the other two, slow and fast diffusion. So for small times, say you begin, small times are the red one, say you begin with the initial data, which is like this, no? The ETH equation, what does it do? Instantaneously, it gives you positivity in the whole domain. So the solution instantaneously, the green one is the, say at time 1, no? The solution spreads immediately, and it is positive and bounded. Bounded how? Bounded, remembering of the Cauchy problem. I mean, for initial times, the boundedness is given by the smoothing effect or ultracontractivity estimate that tells you that, well, you need an epsilon of time to regularize. It's an instantaneous regularization, but you don't arrive at the correct time decay immediately. But for large times, then you have the exponential time decay. So the infinity norm decays like the separate variable solution, and you start to behave, and then you will end up behaving like the separation of variable solution with the first eigenfunction, which is the positive one. Of course, here we are taking non-negative solution always. Okay, so what we have seen that it happens for the porous medium equation is the following. For small time, what happens? Well, there is finite speed of propagation. What does it mean? Look, we start from a compactly supported initial data. This one. At time one, the solution, time one is small times, the solution is still compactly supported, and here at the boundary is just C alpha, so it's not a classical solution. And here it behaves like it doesn't see the boundary yet because of the finite speed of propagation. Then at some point, for large time, it will be positive on the whole domain, and it will converge to, and it will start to behave and then converge to the stationary solution, or in normal variable, it will tend to behave like the separate variable solution for large times. And this is what happens. So here you have to wait for the positivity to take place in order to enter the asymptotic regime. What happens in the fast diffusion case? Well, in the fast diffusion case, what happens is that we get instantaneous positivity. So you start from compactly supported and immediately you are positive everywhere and with a certain boundary, lower boundary behavior. The problem here is the boundedness. Okay, here the problem is the boundedness because, for example, when M is very close to 0, L1 initial data do not produce bounded solution. Okay, so here you need a bit more of integrability to have bounded solution. We will see this in detail, no? And the problem is, okay, once you are bounded, you are positive, but then if you are positive, the diffusion becomes very fast because you are started to diffuse. And what is the problem? The problem is extinction in finite time. There can exist a time, capital T, such that solution is 0 after the time. So understanding the asymptotic behavior in this case, it doesn't mean tau going to infinity, it means tau going to the extinction time. But first difficulty is that the extinction time is not explicit.
So what is the R in the you have a subscript R in the estimate in the middle of the fast diffusion?
Here?
Yeah, what's the R?
R is just the LR norm. I mean, R is any number such that this is positive. And if you notice here, R has to be bigger than N1 minus M over 2. And so when M is very close to 1, it's no condition. R bigger or equal than 1 will suffice. But when you see when M approaches 0, then this becomes N over 2. So it becomes really a condition. No? Basically, there is the Brezi's Friedman counterexample that tells you that if you start with if you take M very close to 0 and subcritical indeed, and you put a delta, then you don't start, then the solution is not, it stays a delta. Okay, and so it doesn't regularize, it doesn't happen anything. So this is a concentration phenomena, which is weird. When M is close to 0, situation really gets more complicated. So this is just to draw a bit of a panorama. I know that I'm being sloppy many things, but I wanted to give the idea of what is happening in the three cases. And you see that somehow the linear case is somehow borderline between slow and fast diffusion. This was just the message that I want to pass with this slide. Let's go back.
So the threshold exponent is 1 minus dimension over 2, where this starts to be a condition. Is that right?
Yes, look, I have written it here. No, you look. The initial data is chosen to be. Now let's start with the proper setting. No, so we are in the fast diffusion equation. We take non-negative initial data with sufficient integrability, exactly this integrability, which is required only when M is below this critical M. This critical M is where you start to lose mass in the whole space. Just to be clear with the people who is familiar with fast diffusion in the whole space. So when you start to lose mass in the Cauchy problem in the whole space, then you need more to be bounded. So here you lose, when you are below these, there are no fundamental solutions. The delta initial data doesn't produce any solution, which is not a measure in anymore. It doesn't produce Barenblatt solutions. So Okay, of course, the mass is not preserved along the evolution, but this is not a novelty in the sense that also in the equation, the mass is not preserved, but here the mass is lost so fast that solution extinguish in finite time. So there exists a capital T, depending on initial data, such that after this time, solution become identically zero. And this is basically a consequence of having Sobolev and Poincar inequalities. So this is a first difficulty. And then let me tell you, long story short, about regularity. So solutions are indeed strictly positive until they extinguish. This is a consequence of Harnack inequalities, which were proven by Di Benedetto, Janazza, Kwong, and Vespri from the 90s to the 2000s. And in the supercritical case, in the subcritical case by Juan Luis and myself. And then once you are positive and bounded, you are regular. And Di Benedetto, Kwong, and Vespri already proved in 1991 the solutions are regular up to the boundary, say at least C1. Here we are assuming very regular domains, C2 alpha, and they're smooth in the interior, they are even analytic. Then there is a recent work by Jin and Xiong in which they prove sharp boundary regularity. So we don't have to worry, solution exists, regular, and they live until they extinguish, and they are very, very nice. So the question now is, what happens close to the extinction time? Okay, this is the question. So what do we do? Again, we rescale, but we have to be careful because now we have many things we don't know. So we want to do a logarithmic time rescaling, the ralenti, to see better the action, and we can do it in this way. But you see that in all these changes of variable, which are simple, I mean, it's just a logarithmic change of variable, we basically zoom the interval 0t in 0 to plus infinity. This is almost trivial, but you have the quantity t, which depends on u0, the extinction time, which plays a role. And it enters also in the constant, which affects the new equation. So here, you lose the extinction time in the sense that in this formulation, after rescaling, solution live for all times. And they have some nicer property, but where is the information about the extinction time? Is hidden in the constant. And we will see that this will cause some problems already here. When you look for stationary solution of this equation, then the extinction time plays a role in the constant. And since here the problem is super linear, we want to have to be really careful. So anyway, the ansatz of separation of variable works, and this is the candidate to be the profile of the behavior of all the solutions which are positive and bounded. So we rescale so that, as in the other cases, the solution by separation of variable becomes stationary. So this is solution by separation of variable, and in the new variables, it will become stationary. Okay, now here a crucial exponent arises, which is the Sobolev exponent. So below this exponent, there is no solution. This elliptic problem doesn't have any solution. So we are restricted to be above this exponent. Okay, so let me state correctly the problem. We are interested in describing the behavior near the extinction time of the solution to the fast diffusion equation, which means basically this. After rescaling, we can state precisely the equation, which is given a non-negative solution to the rescaled FD without bounded, which satisfies the rescaled fast diffusion equation. Is it true that there exists a stationary solution such that W of t converges to S or not? And if there is this convergence, in which sense we have this convergence? And then the last question is, and if it converges to this, can we say something about convergence rates? So these are the questions I would like to address in the rest of the talk. So let me do a bit of history. A bit of history that has to be brief because of the time, but the first pioneering result and where we read about the problem, it was pointed out to me by Juan Luis Vasquez. It was a paper of Berryman and Holland of the 80s. I mean, it was probably the first paper in which the term fast diffusion was used to denote this kind of equations. And probably, I'm not sure, I think that Charlie is in the audience. He can tell us more about this. And they also tell us the story of this paper on a very, very nice email. And what did they prove? Well, they proved that any bounded solution W of the rescale solution of the rescale problem converges to a stationary solution. So there exists a sequence of times such that you have that WTN converges to S along this sequence. So if S is a unique, if the set of the stationary states is unique, no problem. This is a very nice result. So you converge to the stationary solution. But there is the first difficulty. Stationary solution need not to be unique. So the set of equilibria can be made by many, many solutions. So you can eventually converge. If you take two different time sequences, you can converge to different asymptotic states. So this is the first difficulty, which was solved by Feiresel and Simondon in the 2000s, in the year 2000. No? I mean, they say, even if the stationary solution are more than one, the uniqueness in the parabolic problem basically is so strong that allows to prove this, that given a bounded solution of the rescale problem, there exists only one stationary solution such that W converges uniformly to it. So even if there are many states, the initial data selects one asymptotic profile. But this is not explicit. This is a paper that uses Lojasevich's techniques, and it is inspired of it is reminiscent of the technique, or directly inspired by the technique of Leon Simon in this famous paper in which he proves compactness of the orbit.
Sorry, I'm confused. Are you saying that the stationary solution S can depend on the initial data W, or no?
No, I'm saying given given W0, there exists a unique S towards which the solution generated by W0 converges.
So in principle, S could depend on W0.
S depends, yes. If it is not unique in general, S is S of W0.
Thanks.
I mean, given a W0, I can find a unique S, and then the solution converges to that. Okay, this is, but this is not explicit. It's not like on our end that you can choose it in terms of conservation of mass and of center of mass or this thing here. It's abstract. It is chosen by compactness essentially. Yeah.
But somehow it says that if there are more than one S, that there's no boundary separating the W that converges to one S and the W that converges to another S.
Yes, exactly. And this is part of the difficulty of the problem. This is really part of the difficulty of the problem, because, for example, if you are on an annulus, you have the symmetric solution, and then you have one that does symmetry breaking, but then the Laplacian is invariant by rotation, so you have a whole family. And so how do you say that you converge to that one and not to the, I mean, you do an infinitesimal perturbation of the angle, for example, there. How do you distinguish that? The answer is we don't know. You have to use this theorem and work with general S solution to the problem. Okay, so but this we take for granted. I mean, there exists one solution which depends on the initial data. So fixed the initial data, you only go to one stationary solution. This is quite important. And then you can prove, given this setting, so when you already know that you are converging to one, then you can improve the convergence in relative error. And this is something we did with Gabriele Grillo and Juan Luis Vasquez in 2012, improving the so-called global Arnab principle proved by Di Benedetto, Cuonca, and Vespri in the 90s, in which, I mean, this can be rephrased in the following way, like Q is trapped between some constants and the separation of variable solution, basically. So the distance to some power and a certain power of time. And what we prove, what Di Benedetto, Giannazza, Vespri proved, that here there are some constant, big one and small one. What we prove is that these two things, these two constant, converges to one when you approach distinction time. So we do an improved version of this, which amounts to saying this in relative error. And this is difficult because at the boundary they are both zero. So you have to be careful there. Okay. So after this, let me come to the, after this, we were like asking to ourselves, are there convergence rate? And this was a question I posed to Alessio in 2016, I think. And then, well, the answer is given in this theorem. So let me tell you. Define a set O, which is all open and C2 alpha smooth, all open and bounded sets over N with C2 alpha boundary. And then what we prove is that there exists an open and dense set, a good set of good domains, such that the following holds. So what this theorem is generic in the sense that it holds on almost all open domains. I will come back to this later. So what do we prove in such domains? That given the stationary solution, there exist two constants, lambda m and k, such that you have a decay of this quantity. So the L2 norm, the L2 weighted norm of the relative error decays exponentially with this lambda rate here. And lambda is sharp. Also, using regularity, you can have the same result for the infinity norm then, okay? You lose a bit here, but now using recent boundary estimate, you can eliminate this for n here below. And this is this for n is not, it's just by computation and interpolation, but it can be removed by the recent result on boundary regularity that I mentioned before. So in original variables, what you are saying is that this quotient is not just going to zero, but it is going to zero with this rate. And you see that here, the extinction time appears also at this point. So it's like a bit involved. So let me just mention that there were some rates for m very, very close to 1 using continuity argument that we proved in 2012, but this m, although explicit, it was very complicated and didn't fill the whole interval. Okay, so let me now pass to the proof. I have 5 minutes. I will give you just an idea of the proof, let's change notation and let's switch to the so-called elliptic notation. So you just put w to the m equal to v, then the equation is this one, the initial datum is this one, zero boundary data preserved, and the stationary solution becomes the solution of the classical semilinear elliptic equation, which is this one, with subcritical exponent. This is why we have a limitation of this method, because above, when p is too large, there are no bounded solution of these. We don't know what to do. It is not clear what happens there. We need to assume through the proof this assumption that you are small in relative error, but this is really not an assumption. It's just to fix that you are uniformly small, but this is always guaranteed by the convergence in relative error. So given a delta, there exists a T0 large enough such that this is true. So this is not really an assumption, but it's just to fix delta. To say we start from time 100, 100,000, whatever. Then here we have this control on the solution. Then let me just tell you, the stationary solution exists, are bounded, even absolutely bounded. They are non-negative by Harnack inequality. They are regular in the interior and as regular at the boundary as the regularity of the boundary of the domain allows. And they are unique, we don't know. Unique depends on the geometry of the domain. For example, uniqueness holds on ball, does not hold on annuli, and there are several conditions in the literature. I will maybe give some example if I have time. So what do we do? Well, we linearize around the stationary state. So here, as Robert was pointing out before, you have a W0, which now is a V0, and you select your S of V0, which in the new, say, S of W0, which in the new variable, which is this capital V. This capital V is the stationary solution to which you are converging, and it's now determined by the initial data. So we linearize around such solution, and this is the linearization. This is the linearized operator. And notice that V is not a stationary solution of the linearized equation, because there is a P coming into play, and P is bigger than 1. Okay? So the natural question here is, which are the stationary state of this equation? Well, they solve this elliptic equation with potentials. Well, understanding whether or not the above linear equation have non-trivial solution is essential to our method. So we compute the spectrum of the linearization. This is not so difficult. It's essentially the same argument as with the Laplacian, and we have a discrete family of eigenvalues, a discrete family of eigenfunctions with their multiplicity. Okay, and here, just to set the notation, notice that the first eigenvalue, we know what it is the constant C. It is easy to see. And the first eigenvalue is the well, if you want to renormalize it in L2 weighted, okay, you have, it's exactly V, the stationary solution. Okay, so once you compute the spectrum, you try to see how do you get the asymptotic behavior in the linear case. And once we understood this, I can explain in 2 minutes how they give you a flavor of how the nonlinear method works. So you take the L2 norm, you derive it along the flow, and you get what is usually called in this language the Fisher information. But you see, the Fisher information is not necessarily positive. I mean, this is bigger than the first eigenvalue, so you don't know. What do you need? You need an improved Poincaré inequality, which is an entropy production inequality, if you want. No, you need an improved inequality. You don't. It's not enough to have it with the first eigenvalue, and so you need to impose suitable orthogonality condition as for the equation if you want to converge to the second eigenfunction, for example. So what you want to do is to use the classical Gromwell inequality, which is you derive the entropy, you get the Fisher information, and then you use the Poincaré, and then you conclude exponential decay. Yeah, fine, but we need first some condition. First, we need to say that there is no non-trivial solution to the elliptic equation, to this elliptic equation. And then under this assumption, we can see that then PC is not an eigenvalue. So you impose the orthogonality condition up to here, and you get the improved Poincaré. You have a small gap here, you see? And this helps you to show, well, this helps you to give exactly the exponential decay that you wanted, but you need some orthogonality condition. Well, fortunately enough, in the linear case, the orthogonality condition are preserved along the flow. You just do this, no? You multiply with the eigenfunction. Here there is a weight, but there is no big deal. You get the equality, and unless at the initial time the orthogonality condition was prescribed, this blows up exponentially in infinite time. So you really need the orthogonality condition to show convergence to zero of these solutions. You really need to impose those conditions. There is a problem. In the nonlinear case, suppose that you can prove an improved Poincaré inequality, the orthogonality conditions are not preserved along the flow. So this is really a problem. Well, let me just tell you that the assumption that we do that there are no non-trivial solution of these, or equivalently that CP does not belong to the spectrum of the linear operator, is not so easy to check in general, and it can be false in general. But what we learned by a beautiful paper by South and Temam of 79 is that this thing, assumption H2, is generically true. What does it mean? You take the family of all the open set, regular open set. You define a topology, which is the C2 deformation of the set. And then with this topology, there exists a open and dense set, G, the set of good or generic sets, such that H2 is true. So this assumption is true on generic domains. What does it mean practically? Well, when I asked Alessio what this means, he told me basically any domain that you can actually draw, because you cannot draw a perfect annulus, any domain that you can draw, it goes. Okay, so if in the annulus this is false, you perturb just a tiny bit of the boundary and it works. This is the practical way of understanding this. And this is why we say on generic bounded domains, because we really need this to be true. Then H2 holds on balls over n. H2 holds on domains which are convex with respect to certain direction. Then it holds for C1 perturbation of the ball. Then it fails on annuli, but it holds on C2 alpha small perturbation of the annuli. Then it holds for P close to 1. There are a lot of cases in which this assumption is true. Say
Sorry,
almost
when you say it holds for C2 small perturbations of the annuli, you don't mean for all C2 small perturbations. You mean there exists small arbitrarily small perturbations.
Yes. Basically, when you break the symmetry, if the domain is too symmetric and it has a non-trivial topological, then you have problems. But this is related also.
But the genericity result that you described by Sout and Tamam, it doesn't say. I mean, there could be zillions of nearby domains that break with broken symmetry that violate the hypothesis, but they fall outside this open dense set.
Yes, exactly. So, so let me go to the nonlinear entropy methods and tell you that this is really where Alessio came into play. And I have a proof of this. You see, this is him at the blackboard in Austin, in his former office at Austin, in a very sunny day. And we were attacking this problem. So what do you do here? You try to repeat the same in the nonlinear. So you define the nonlinear entropy. It is comparable to the other one, but since I have no time and I thought this would be the case, let me just show you a slide in which you have the linear operator and the nonlinear one. You have the linear entropy. We already saw how to apply the entropy method here. So we try to mimic the same. So we define an entropy, and this costed us months, because it's now when you see it, you see, okay, it works and it's nice, but it is not the standard entropy. It's not the first order. You see here, you don't have the standard Taylor reminder, but this is the entropy that worked for our purposes. And when you derive the entropy along the flow, you have the Fisher information, which is essentially the linear one applied to F, which is the difference. F is a notation for the difference here, plus a remainder term. And the remainder term, which is cubic. Okay? So on one end, we define this entropy, which is the integral of a convex function, by the way, which is comparable in the asymptotic regime to the linearized entropy from above and from below when you pay a small constant. I mean, this constant is asymptotically sharp. When delta go to 0, this becomes inequality. And then what do you want to use? You want to use the improved Poincar inequality, which are these, but you need some orthogonality condition. And the orthogonality condition, we have already seen that they can be problematic. So what do you do? Well, we invented the idea of almost orthogonality. So you take this kind of quotients between the projections, the weighted projections, and the entropy, the linear entropy. Okay, if this is small, then you can still prove an improved Poincar inequality. So with this quotient small, you still got a spectral gap. You still got an improved spectral gap, which is what we got here. You see, you have the improved spectral gap, and you pay an epsilon price, but it's still okay because epsilon can be chosen arbitrarily small. Okay, so here you have the improved Poincaré that allows you, once you plug it here and you estimate the cubic term, remember, is smaller than delta times constant, you obtain the following entropy production inequality. So E prime is less than positive constant, and then a small price that you pay here. And this already gives you the decay, an exponential decay of the entropy, which is almost sharp, almost. You pay this. You have to work a lot more to prove what? That the almost orthogonality is preserved along the flow, the nonlinear flow, and for this you need to introduce some nonlinear quotient, compare linear and nonlinear quotient, and do a lot of stuff. But really, where Alessio made an amazing proof, I was really impressed. It was to show that basically, if you converge in relative error, then you are almost orthogonal always. And this, I conclude with this, oops, sorry. And this, let me conclude by going back to the slides, is, you see, the almost orthogonality is written here, the almost orthogonality. It can be expressed by means of nonlinear quotient. This was a brilliant idea of Alessio, to invent this nonlinear quotient, which are essentially equivalent along the flow, you see? And so if these quotients are small, these quotients are small and vice versa, so the two assumptions are equivalent, and under this assumption you can prove and improve Poincar inequality and an improved entropy production inequality that gives you the exponential decay. Then we could do more, and this was really amazing. It was in Zurich that Alessio figured this out. If you can control the relative error in terms of the entropy to any power here, eta here is really not relevant, then you end up with this ODE with delay. You see, here the ODE is with the function of delay that fortunately enough we are able to solve, in the sense we find a super solution, which gives you the sharp rate of convergence. The only thing that you have to check is this smoothing effect, kind of smoothing effect, and this is the last part of the paper that we checked. Let me tell you that the most difficult part of the proof was this, to show the possible blow up when the almost orthogonality fails. And we built a quantitative contradiction argument. This is Alessio's specialty. And we were able to show that if you converge in relative error, then you are almost orthogonal with all of these. I'm finished. Sorry for spending more time than what I could. Thank you very much for your attention. And again, congratulations, Alessio, for everything, I would say.
Well, thank you, Matteo, for this beautiful talk. I guess we have time for a couple of quick questions.
So if you tried to do something like an invariant manifold theory, could you avoid the genericity condition on the domains?
Oh, I think that this is a good idea, but it is quite difficult, I think, to describe this invariant manifold here, because you see the equation here. Let me go back to the other slides. You see the equation here is not semilinear, so it's here you have a v to the p, which is, if you write in the other side, a weight which depends on time. So it's I mean, I don't know if Alessio has better feelings about this, but I wouldn't know how to do it somehow, because the fact that there is a v to the p here complicates a bit life in this. If you want to treat it as a semilinear equation, I mean, if this is what you had in mind. I don't know if I answered the question, but basically I don't know how to build invariant manifolds here. But it would be certainly a good cause. And let me mention that there are papers of Goro Akagi in which he analyzes, for example, the case of Anoli and how other solution can attract this, say, symmetry breaking solution can attract some others. But it is all these results are really built on specific examples. No, so here I think we give the general idea of what can happen, and sharp rate, which in the case it happens because sharp we claim because it's the same as the linear one. So I don't have a.
I mean, for non-generic domain, you could have zero. I mean, you could have CP in the spectrum, right? And then you don't expect. I wouldn't expect exponential convergence. So
yeah.
Can't I, but if I look, don't I just go to the next eigenvalue and sort of look for a higher dimensional, what do you call it, sort of stable manifold? I just want to, so okay, if it's in the spectrum, then I just put that into the state. I just look at a higher dimensional manifold and measure my distance to the higher dimensional manifold.
The problem is that it's nonlinear, so it's not that we impose orthogonality. I mean, we cannot impose it, right?
Yeah. No. But there. So, for example, Christian Seiss has done this for the whole space problem, and Herbert Koch as well. So you don't try to say what the manifold is by imposing it. You just say there exists a manifold, and the dimension of the manifold is the number of eigenvalues below the threshold I'm looking at, and then my distance to that manifold is going down at a certain rate.
Yeah, I don't know, because in this case everything converges in a posteriori, right? I mean, even if there are some eigenvalues, they all disappear because the parabolic is stronger than the nonlinear is stronger than the linear, right? The linear could blow up, but the nonlinear doesn't blow up. So everything converges. There is no lower dimensional manifold here. I don't know.
But
I mean,
no, the lower dimensional manifold would count the number of possible end states W, or whatever. I think it was called W. So there'd be a certain number of W's. So for example, if I think about the blow up problem in the, I don't know, the thin film equation, you can't say exactly what point in space or time that the solution is going to blow up at. So if you have n space dimensions plus 1 time dimension of uncertainty. So there's an n plus 1 dimensional family of possible attractors. You don't know which one you get attracted to, but you converge to one of them in the end. And then you measure your rate of your distance to that n plus 1 dimensional manifold, and that's the thing that goes down exponentially in time.
I'm not sure here it's the same, but I don't know. Maybe Matteo.
We should check.